Good morning, I'm Gabriel Bernardino, a researcher at Clarysse, Lyon, France, and I will present my work entitled Hierarchical Multi-Modality Prediction Model to Assess Overweight-Related Remodeling. I will start by presenting the clinical problem, which is multimodality in cardiac image assessment. So there are several imaging modalities for diagnosis, but they have different quality and different cost. For instance, MRI has better image quality, but it's also less available than echocardiography. So the clinician has to ask which modality to choose, and usually his reasoning is qualitative and argumentative and is recapitulated in clinical guidelines. On the other hand, there are machine learning methods that will fuse all information. However, they require both acquisitions to be acquired, and therefore they are very data intensive. Our contribution is a model to predict whether it is better to acquire a more complex acquisition or if a simple acquisition is good enough to do a diagnosis. So here is my framework. So I will be working on a classification, therefore there is one level Y that I would like to predict. And for that I will have some features, so some simple data, X0, and some more complex one, X1. And we have two classification models, one for X0 and another one for X1. And this will be based on the Gaussian process classifier. This was an arbitrary decision. And the important thing and the novelty is the weight W, which will tell us if the simple data X0 is enough, or if we would like to acquire the X1 data. And in order to make that X0 can predict W, we impose a Gaussian prior on W. This setting can be seen as a probability, which can be maximized using the classical optimization methods. So, in order to make the prediction, sometimes we would make the prediction without having to acquire X1. So, the setting will be the following. So, we will predict the weight, which we will be able to do it for each individual given X0. And if this weight is above a threshold, then we will make the prediction only using X0. And if it's below, we will acquire X1 and do the prediction. Thus, changing the threshold key, we can see if we want more or less acquisitions on X1. We will verify this using a toy dataset. This will be formed by three features, F0, F1, F2, which will be distributed into the X0 and X1. X0 will have F0 and F1, and X1 will have F2. And we will have a label which will be positive if F1 plus F2 plus F3 is positive. And to make things more interesting, we will change some of the labels at random, creating regions where there is no information, and therefore it doesn't matter if we acquire X1, we will still have the same uncertainty. And here it's our proposed approach in X0. This is F0, this is F1, and this is F0. And we will see that there are in purple the regions that our model thinks that it's more interesting to acquire X1, and in yellow the ones that he thinks it's not interesting to acquire X1. We can see that near the decision boundary in brown, there are these two clusters of purple where there is a lot of sense to acquire the more information and be more sure whether the label is 1 or 0. But however, in the center, our method correctly identifies that there is no information to be gained. In spite, the classical methods, which is uncertainty, so the typical approach would be to get a classifier from F0 and F1, see if, in which cases there are more uncertainty, and for those cases try to acquire X1. However, this will include the whole decision boundary, including the points where there is no information to be gained. Therefore, this method will propose acquisitions that will have no benefit. Now that we have verified our method, we will apply it for an overweight data set. Here, we'll try to compare MRI and echo and see when it's more pertinent to use MRI or echo. We will have a small population of 147 individuals, and we will have a first level X0 consisting of 4 echocardiographic measurements and X1, which more complex one, which is MRI biventricular shape models. So we will simplify the X1 by applying PCA and keeping the fifth modes with higher variance. The level that we need to predict is overweight. It's defined as BMI greater than 25, and it's kind of the transition zone from an adequate weight to obesity. The data that we will have is all geometric and only regarding diastole. There is no functional data whatsoever. The first result will be to apply the classification model with different data. For instance, here we have the X0, the echocardiography, X1, the MRI, X0 plus X1, which is all the echocardiographies and MRIs, and our hierarchical data, which will consist in some cases for echocardiography and in some other cases of echocardiography and MRI. Surprising result is that the echocardiography outperforms MRI. This is not caused because echo has better image quality than MRI. We know that it's not the case, but however, remember that we are working with overweight, which has a global effect on the heart. Therefore, the measurements are an adequate way of characterizing overweight, while the shape models, which are very regional, may be a way too complex model, and therefore we are losing predictive power. However, if we combine X0 plus X1, we see that there is a boost in the classification accuracy, and this is the same whether we use all MRIs and all echoes or if we use our hierarchy. And our hierarchy allows us to have the same AUC as the combination, but then we only use 30% of the MRIs. This means that we can get the same confidence in our results, but however, at a much lower cost. The last result will be to see if we can say something about which individuals can benefit from MRI and those who can't. And for that, we have a plot in the X0 space. We have a color map with the weights. This means that the weights in purple, it means that it's pertinent to acquire MRI, and in yellow, it means that it's not. Firstly, we can see that there are those two clusters of yellow far from the decision boundary. The decision boundary is this line in red. This means that far from the decision boundary, our model is already sure of whether it's an overweight or not, and therefore it makes no sense to acquire the MRI, since it's already quite sure only with echo. If we look near the decision boundary, we see some interesting pattern, which is that in the upper part there is a more purple, while it's more greenish in the lower, meaning that our model identifies the individuals in the upper part as the individuals who have a better benefit from MRI. So we get two points. A red one representing the individuals that high benefit from MRI, and one in blue, which is the ones that do not benefit as much. And what we can see is that the individuals in red have higher systolic blood pressure and left ventricular mass, indicating that they have a more pressure overload and hypertrophic remodeling. To finalize and conclude, I have presented a hierarchical methodology for quantifying the benefits of complex modalities over simple ones. This has been illustrated with the dataset of overweight, and as a future work, I would like to extend this framework to several modalities, and I would like to learn the data hierarchy instead of applying an already known one. Finally, I would like to thank my co-workers and funding agencies. Thank you very much for your attention.